Talk of the morning is Marco Carmosino talking about learning again.
Yep, more learning now. Thank you everyone for having me for this. So this is joint work with Eric Benedict, who's at UCSD, Russell's PhD student now. I'm Marco Carmosino, I'm at IBM. This is Antina Kolokolova at MUN, Rami Ramya at NMT, and Manuel Sabin, who was affiliated with UC Berkeley when this work was done. Okay, so learning with distributional inverters. What is that? What am I talking about today? This is just one weird trick that is going to reduce learning in a variety of settings over efficiently samplable distributions to learning over just the uniform distribution. And we'll give a concrete application of that and a generic application of that in this talk. And it is literally a 3-step reduction that works in a bunch of places. So I just want to show it to you on the whiteboard. And that's our plan for today. Okay, as usual, the motivation is to advance learning of simple concept classes, where simple means that we can prove complexity lower bounds against those classes without working too hard. And today that'll mean the natural proofs barrier, or the existence of distinguishers for pseudorandom functions in that class. But the specifics of this are not going to come up at all. What did come up already in this workshop, thank you, Haley, for letting me reproduce this slide, is a reference to the generic version of this work, where we go from natural properties to pack learning over any fixed polynomially sampled distribution, that's us, with membership queries. And again, to elaborate on our plan and explicitness today, this is, thank you again, Haley, for letting me take a look at these slides. They get from the stronger assumption that MKTP on the uniform distribution is an average BPP. They get white box access to the distribution, and they get random examples, which is amazing. This, as far as I understand, it's a huge open problem to do this with just MCSP or just a natural property. We just have a natural property. We do get fixed distribution learning, and I will be very explicit about this notion of white box access that we need for the sampler, show where it comes from, and it's part of this reduction. Okay, so that's the setup. That's another place where it shows up. And let me be more concrete about our results. So first, we start with the concretely specifying the concrete results. We can query learn AC0 mod P. That's, I'll define the circuit class later, but constant depth circuits with counting mod P gates over concise product distributions. So what is that? We get query access to a function in the target concept class. We get randomized quasi-polynomial time, and we get this explicit list of biases of the product distribution pi. So that means that you have n bits. Each bit has probability p sub I of being 1 independently. You sample each bit in sequence. That is the type of distribution that we can learn over, where previous work only learned over the uniform distribution. So this is like some small departure from the uniform distribution, but it is progress. Yeah, and we output a circuit H approximating that function when fresh inputs or challenges are sampled from the product distribution that you told my algorithm about in advance by sending over these biases. Okay, now we have some conditional results. If there are natural proofs of circuit lower bounds, then we can query learn Boolean circuits over polytime sampleable distributions, where we'll depend on the code of that distribution in a way that I will be super explicit about when we come to that part of the talk. Given query access to the function, randomized polynomial time, and the code of a polytime sampler for the example distribution, we can print a circuit approximating F over that distribution. So when examples are sampled fresh from mu, we get exactly this condition over here. Okay. So those are the results. Here's our plan. We're going to do just quick statements of prior work on learning circuits in this setting, both concrete and conditional. We're going to sketch our algorithms, and we're going to conclude with some open problems that I think are exciting, especially here, because conditional constructions of better cryptographic primitives will let us expand the scope of distributions that we could learn over and make the conditional results better too. And I hope that it's crystal clear once the talk is over how and where those open problems plug into these pieces on the whiteboard. Okay, so I don't even need to, going on the last day of this workshop, right before lunch, I don't need to tell you what this circuit is, right? It's a DAG, we have and or not gates, and it's the worst thing in the world because we don't know anything about them. So the key idea in this work is, again, has shown up all over this workshop. We're going to exploit the sometimes implicit, sometimes explicit constructivity of proofs from complexity theory and cryptography and chain those together into learning algorithms. Okay, so circuit classes and lower bounds. Again, very quickly, here's AC0. It has and or not gates. We restrict to polynomial size, constant depth, unbound and fan-in. The lower bound is parity. So what's the next thing you do? You add parity to your gate set and you get the next circuit class, AC0 mod P or mod 2. And for Q and P distinct primes, we have that the mod Q function doesn't have AC0 mod P circuits. That's the classic result of Rasbarov-Smolensky, and a natural property can be extracted from that. Very good. Okay, so let's put the learning algorithms side by side for these classes. LMN 1989, given sample access to a function in AC0 and randomized quasi-polynomial time, they can output a good approximating circuit over the uniform distribution. How do they get this? They use a Fourier decomposition or bounds on the Fourier spectrum of any function in AC0 that, importantly, they extracted that decomposition and those properties by hand from the circuit lower bounds against AC0. In my previous work with Antonina, Valentine, and Russell, hello, we given query access to any function in AC0 mod P and randomized quasi-polynomial time, we can output the same kind of approximator, and we use natural properties, the natural properties from the previous slide, circuit lower bounds here, to somewhat generically construct this learning algorithm out of a variety of distinguisher to predictor constructions. And yeah, I just want to emphasize that these match almost everywhere except for the query versus sample access and the specific hand-tuned learning algorithm versus, okay, we drop the natural proof into this construction and we get an algorithm. Good. Okay, so let's take the next step. The uniform distribution is not the only distribution in the world, or so I've been told by people who actually do learning. FSJ 91, they were able to learn AC0 over product distributions. So same access conditions, and then they also get a list of the biases. So this is that kind of fixed distribution learning setting. And they're able to output a circuit that approximates the target concept well over this product distribution that you're given explicitly. Great. Now, how did they do it? They actually gave two different algorithms for this in the paper, and they're both quite nice. The first one is a kind of a generalized Fourier analysis of LMN, where they switch up the basis of that the algorithm like finds heavy Fourier coefficients in to account for the biases in the product distribution. That's very cool. And then they go in by hand and they reduce LMN over this specific product distribution to LMN over uniform. Okay, so in this work, what do? We learn AC0 mod P over product distributions concretely, given exactly the same kind of access, except the queries, which we can't get rid of. we output the same style of approximator circuit, and the algorithm, there's no way this is going to work, right? So we're of course inspired by FJS 91. This is what we start with, but the previous algorithm CIKK has nothing whatsoever to do with the Fourier spectrum of the functions. Indeed, it can't, because these classes, they have parity right in them of unbounded fan-in. So this is a non-starter. So what we do instead is we generalize exactly this. Instead of reducing LMN specifically over a product distribution to LMN over the uniform distribution, we reduce learning over product distributions to learning over the uniform distribution. Okay. So let me sketch this really quickly, and it's nice because it's simple. First, I'm going to tell you what a sampler is. So mu is going to be a distribution on n-bit strings, and we're going to have an efficient procedure that takes our bits of input, the coins for the sampler, and it samples from mu if for every target string in the range, the probability distribution giving the sampler like true random coins is exactly the mass of X under that distribution. So S sub mu is going to map random coins to strings distributed exactly according to X. The class of these that you can do efficiently is called psam. And given this definition, we can imagine a very natural definition of a sampler for a product distribution, right? Just write down the coefficients and sample proportionally with rejection sampling. It's very efficient. Okay, so here's the pseudocode for learning. Let's suppose that we've got some target function inside an example oracle, F, and it's also inside a concept class that we can learn, lambda, over the uniform distribution already. Now, let's say I'm going to be very cavalier about this for now, and then very specific. Let's say we have some I sub mu, an inverter for the sampler. So if does this have a, yeah. So if I get something from the range of the sampler, I can get something from the domain of the sampler. I can turn samples into coins. It's an inverter for that S sub mu. And yeah, and I have that lambda is learnable over the uniform distribution. And finally, I have one of these composition properties, right? So if I take the sampler from mu and I compose it with my target concept, I can name that, that's a new function, G of Z. Note that this now goes from sampler coins to decisions, not from examples to decisions. And let me have G inside my target concept class, okay? So so in particular, if the sampler was already inside lambda and lambda is closed under compositions, I can have this. What are we going to do? We're going to use the inverter to recover our coins and call our learning algorithm over the uniform distribution. So step one, we're going to learn G over the uniform distribution on R bits, which is appropriate coins for the sampler. And now let me start being explicit about stuff like, where do I need code? Over here, I need the sampler code to simulate G, right? Because I've got an F oracle. I don't have a G oracle. But if I've got the code for the sampler, I can just say, okay, learning algorithm, whatever you ask for, I'm going to first plug that into the sampler and then plug that into a query to F. So I can simulate this no problem with an F oracle, and then observe that my challenges, right? My fresh inputs that I measure the quality of my hypothesis with respect to, those are distributed by lambda, just according to the setup of the learning problem. So at the end of this algorithm, very simple, I print my hypothesis is the hypothesis that came out of learning over the uniform distribution with the inverter hidden inside of it, okay? And this is the second place where I'm gonna need the code of the sampler, because the construction of inverters that we use has to print the code of the sampler into the construction. So code of the sampler shows up in exactly this is what white box means on Haley's slide. It means that I need the code of the sampler to simulate these queries, and I actually need it to shove into this inverter over here that will be output as part of my hypothesis. Okay.
Choices for this ISMU, like, do they matter? Does it matter?
Yes. Anything. Okay, so you're jumping ahead a tiny bit, but yeah. So are there any questions besides what kind of ISMU do we have? Because I think at this point the idea is like very clear and straightforward.
So if you're not shooting for proper learning, it's still important that S of mu be in the class, or at least the composition be in the class. But I sub mu is just used in the output.
Yes.
And you don't have to actually have I sub mu in the class.
Yeah, that's a very good question. So if I'm not shooting for proper learning, I sub mu can be any efficient circuit because I'm allowing my hypothesis to be as complex as it needs to be to do the job. So for example, in our setting, we need an NC2 circuit to execute the natural property against AC0 mod P anyway. So this already has an NC2 natural property stuck inside of it. So additionally, putting the inverter from Impagliazzo and Luby doesn't hurt too much. Yeah, this is where we need efficiency. We need, if we're not doing proper learning, we need the sampler to live inside the target concept class. Okay. So, and then Ryan, next slide will come to, look at this. This is doing an awful lot of work, right? This definition of a good inverter. So let's unpack that and apply it together to this problem. The conceptual message is that we picked out a definition of good inverter from classical cryptography such that this pseudocode, quote, just works. And the interesting thing about what FSJ 91 did is they had a different definition of good inverter that wasn't quite as powerful as this one. They actually had like kind of a hand-tailored definition of good inverter that was kind of very close to what LMN was doing anyway. And it turns out that if you just take this additional step of abstraction, their idea generalizes. So this is distributional inversion from Impagliazzo Luby 90. One-way functions are essential for mini-crypt. Basically, we get statistical simulation of coin image pairs for those samplers. And really the only technical components here are either conditional or unconditional constructions of distributional inverters, because we have to get them from somewhere. And we kind of give this proof of concept for reductions from learning samplably to learning over the uniform distribution. And this induces a few partial answers to some questions that FJS 91 had. So one question was, this is very natural, is AC0 learnable over AC0 SAM? Like that seems kind of reasonable, right? And the answer, well, if there's no distributional one-way functions in there, then yeah, we can run our reduction on LMN. But that's all you need to do. And then the question, they also asked, like, when in general does inverter learning work? Because they did have a like specific definition kind of cooked up for LMN. And we can just say whenever a mu sampler is distributionally invertible and fits inside the target concept class, so that the original algorithm still works.
Give a sense of why do you think it's reasonable that AC0 does not have a distributional one-way function?
Oh, I have no idea about that. That's one of my open questions, actually. I don't even know if NC0 should. Thank you. Yeah, we'll come to that at the end, where I talk about efficiency of building cryptographic primitives from other cryptographic primitives. Those are obstacles for this approach to work in general and in specific cases. So yeah, great question. I have no idea. I just know that this is one way to answer this question. Determine whether or not AC0 has distributional one-way functions in it. You could.
If it does that imply a no answer? No.
I think it does. Like I think that you can build a distribution that's hard to learn over inside AC0 samp, even though you can learn over AC0 uniform with ln by existing. So I think yeah, I think so, but I'm not completely sure. I will think carefully about that and get back. Okay, so what exactly is a good inverter and how do we use it? This is statistical indistinguishability. I'm going to have two distributions, mu naught and mu one. They're on m-bit strings. I'm going to have some delta between 0 and 1. Then I say that these two distributions are statistically indistinguishable within distance delta if for every t that's a subset of 0, 1 m bits, you can't tell them apart using this test. The probability that a string shows up in t under mu naught versus mu one is delta close. So what this says is not even an information theoretic adversary, like an adversary who knows this set t that may be very difficult to construct, can distinguish these two distributions by looking at them. So what you can do is define distributional inversion of a sampler based on this statistical distance notion. So let I sub mu be an efficient randomized TM, and I'm going to suppress dependencies on the size of the examples that we're sampling and the coins of I mu for legibility here. But this is the important part of this definition of distributional inversion. What it says, where Z is sampled according to U sub R. So first, what does this mean? This is legitimate coins for the sampler. This distribution, the circle is concatenation, is legitimate coins for the sampler and the output of the sampler. So this is input-output sampler pairs. Over here on the other side, I've got a legitimate sample from the sampler. And then over here, I've got, okay, we ran the sampler and then we wrapped it in the inverter. So the inverter is, remember, is sending n-bit strings to r-bit strings. So this will also type check, right? It'll look like an r-bit string, n-bit string pair. And then this just says that these pairs, this distribution over pairs is statistically indistinguishable. If you want to be very precise about the difference between what we were doing in FSJ 10, they had a condition that only controlled, that didn't control pairs. But this is the right notion from Impagliazzo Luby for enforcing niceness of the distribution of outputs of the inverter. Okay, and what are we actually going to do with this? Our reduction is that we're just going to substitute fake coin sampler pairs from the inverter into the correctness condition of learning over the uniform distribution, right? So our adversary, in some sense, is the correctness guarantee of learning over uniform. And now we're going to switch to being on the whiteboard for a little bit while I discuss that. Okay. So step one over here is I have to define a statistical test that corresponds to the correctness of my learning over uniform algorithm to fool with this inverter. What's that going to be? It's just going to be error sub h, so that's the error fixing h of z compose x is going to be the set, sorry, z concat x of z concat x's such that my hypothesis on z disagrees with my function on x, okay? This is appropriately typed. It's got coins and then examples. It's a statistical test. So step one is we just substitute this error test into the I sub mu into the correctness of the inverter, right? We have this bound on the TV of any test, so we can sub in error over here, and we get this statement. This is completely mechanical. We just unroll the definition of error to these indicator functions for the set. And then, oh, let me remind you of what the definition of G is. G is the faked up target function, recall. So G is F composed sampler for mu on Z. Okay. So we can continue reasoning completely mechanically. Let's take a look at these two terms. This is the probability over random Z of this inequality happening, but by the sampler condition, this is just X distributed according to mu. So is this by correctness of the sampler. This is our target function G, right? So what do we do when we just collapse these? We get this, which is way nicer. It says, okay, this is the gap between this function over here, H inverter inside versus f of x, agreeing on the example distribution mu with the target concept versus H disagreeing with g of x over the uniform distribution. And we have a bound on this from the correctness of learning over mu. This is at most some alpha. This is exactly the hypothesis that we output. So just rearranging things again and rewriting according to definitions, we get that the probability when you sample in a fresh X, a challenge from mu, that are H prime of X is wrong is at most like alpha plus delta, right? So we sweep in the error due to the errors combine additively. Error due to distributional inversion not being exactly that pre-image distribution, and error from the correctness of the original learning algorithm. And we're done. And this is like stuff like this has shown up in a few places, and it's just really nice because wherever you want, if you have one of these conditions that's relating yeah, you can fool correctness guarantees. You can fool in later work with Ari. We extended this one weird trick to also handle a random example distribution. We can statistically simulate those queries as well and like fool the fact that the algorithm expects samples distributed according to one distribution, but not another. So any questions about the one weird trick part before we wrap up?
Why do you need why can't you learn the product distribution? Why do you need like your algorithm, I guess this isn't about the one weird trick, but right, you were given the biases of each bit explicitly. You can't just like learn this from.
Probably.
The direct product of the statistical distance blows up very quickly.
Yeah. So because we want to be operating with like n many dimensions, like the accuracy of that goes down quickly. So like maybe we could think about that, but we're operating in the scenario where the distribution is given to us as code. That would be interesting to think about though. There's connections, like David Shao has these learning to create versus learning to decide material that I want to take a look at here. Yeah, thank you. So question. Couldn't we just estimate these guys? Okay. So yeah, where do distributional inverters come from? They're from uniform adversary mappings that we pull out of complexity and cryptography. So at a very high level, we can go from natural proofs to no pseudorandom functions to no pseudorandom generators to no one-way functions. And then from an adversary for any one-way function by Impagliazzo and Luby, we can construct an algorithm for distributional inversion of any target candidate one-way function. Okay, so this is sort of the positive direction of all of these constructions. Now you might be saying, hang on a second, something doesn't add up here, right? Because if we can do this, then why do we only learn over concise product distributions and not like, I didn't even give you AC0 samp. I just gave you specifically concise product distributions, whereas generically I said, can't I do P samp if you give me a good enough natural property? Well, let's take a look at the contrapositive direction of all of these connections. What's that like? You start with something called a distributional one-way function, and then you add some circuitry to it, right? You go backwards and you get a one-way function that kind of runs multiple copies with a hashing of the distributional one-way function. Okay, then you take this, you add yet more circuitry on top, going backwards again, you get a PRG by beautiful work of Hill. Okay, you take this, you do some kind of like tree construction, and now you've got a PRF. And by the reverse direction of Razborov-Rudich, that means natural proofs don't exist. So this is why we don't believe in natural proofs for general circuit classes, because if we believe in the very weakest primitive for cryptography, if we believe we live at least in mini-crypt, there's no natural proofs. Tree. How deep is that tree? Tree's linear depth. So let's say I start off with a distributional one-way function or a sampler and say AC0 or even AC0 parity. I'm chaining together these arrows. I'm trying to build up my adversary over here. The pseudo-random primitive escapes my complexity class when I apply GGM. So I cannot generically target an example distribution that is sampleable in AC0 or AC0 parity. This is kind of like this sweet spot paradox that's similar to the reason that you can't directly deploy CIKK against AC0. You need at least the Nissan-Vigderson designs in the target complexity class. It's exactly the same problem showing up in this setup. So what did we do? We wrote the inverter by hand and plugged it into the reduction. We proved it was a distributional inverter. Yeah, because generically we incur Lin depth overhead when we follow these chains. And yeah, that's pretty much. Oh yeah, Rahul?
Yeah, so is the GGM tree construction, is that the only problem in this step, or do any of the other things add blow up that might take you out of AC0 for some hashing in AC0?
Yeah, you can't.
You can't do hashing in AC0, but AC0 mod 2, right? You could.
Right.
I think that if
okay.
Bigger class.
yeah, if you wanted to shoot for that's an excellent question, because if you wanted to shoot for AC0 samp, other steps also kick you out. But if you want to shoot for AC0 parity step, I think GGM is the only blocker there, right? Like low depth.
Hill is already to go from stretch one. Okay. So Hill gives you a pseudorandom generator that gives you like a very small stretch. And then you use generic, I think it was Blum-Macaulay maybe, to increase that. But maybe it was also in GGM. But the first part of GGM was to say, oh, if I even have like stretch one, I can just iterate that. But that iteration is inherently sequential.
Yeah, it's a composition, so that already kicks you out. Even
So
before
that
the tree.
already kicked you out, yeah.
Yeah.
So the tree is actually making things better for parallelism. But
So
I thought the tree was linear depth though.
it's linear in the input side,
Oh.
but not in the seed.
Okay. Oh yeah. Yes. Okay.
So it depends what you want.
So Marco,
Um,
do you think you could say some sort of like either or thing, where like either there's like a black box low depth construction, or sorry, like maybe you can get some sort of barrier saying that if there is no, that if you were able to do a black box construction of a PRG, of a PRF from a low stretch PRG, then some of these, it would break some hard to learn thing in AC0 sample. Does that make sense? Or
That would be great. And that's like, something like that is on my open problem slide. So thank you for doing my open problem slide for me. And yeah, I'll sharpen this up. Thank you. It's much better to have exactly where the obstacle is. I guess I got distracted by the tree. Okay. So open problems, get this working. Like get these generics working below linear depth. And I guess the real, the first stumbling block is already the composition to increase the stretch of the generator generically. Maybe there's more natural distributionally invertible example distributions. Like there are things like Gaussians that people in the world care about that aren't the product distribution. Maybe those have tiny samplers and distributional inverters. Like you can kind of see these settings as like parametric assumptions, right? Like you're saying that, okay, my distribution comes from some family and in a uniform description of that family, but maybe I can identify, so you don't have to solve the whole problem of inferring all the parameters of the distribution. Maybe you can smoothly identify, I'm facing one of these distributions and then invoke a family of algorithms. Product distributions are bad because they're not kind of robust under that inference problem. There's not that reduction that you would hope for here. So maybe we can find a nice example. This, Rahul, I think this goes to your question. Can we develop conditions under which you can't even distributionally invert NC0 samp and learn against that?
Isn't like if you have a one-way permutation, then it's also a distributional one-way function, right? And we have, assuming factoring is hard, we have one-way permutations in NC0. So doesn't this?
Does that go down to NC0 via the randomized encodings? Okay, great. Then they totally do. Awesome. Thank you. Yeah, I really come from complexity theory. And finally, you know, can we do like less white box access to this distribution? The code appears in two places, in the inverter and in the simulation of queries. Can we get rid of at least one of those or get a collection of these or something similar? Oh yeah, and finally, it would be great if we could learn AC0 mod P from samples, but that's a big open problem, I think. Yeah, thank you very much for your attention.
We have time for maybe an hour of questions. Well, then maybe we'll have lunch. Thank you. Back here at 2:15.